Hey guys, just want to give you a quick tutorial on this question 3 of assignment number 5. Okay, actually it's not that difficult. I just gotta do it in the right way though. Okay, so this is basically a Lagrange multiplier or constrained optimization problem. The here we have a plate, and temperature on the plate is this function. The plate basically considering the ant is working on the plate, and then the ant is working in around the unit circle. Okay, so basically the constraint is x squared plus y squared equal to 5. Okay, and we want to find out what's the highest and lowest temperature that ant encounters. Okay, so here's the objective function. Okay, here's the constraint. As we learned, we're going to we can form a Lagrangian here, or Lagrange function. So that's x, y, lambda. Okay. The function is formed by this t, x, y plus lambda. Like this. Okay, so Lagrange multiplier is the lambda here. And the first derivative test to find the stationary point. So basically we need to calculate the gradient of L to be 0, right? Yeah. And that means partial L over partial x. Okay, maybe we'll just put it down here. So 4x squared, 4y, y squared, plus lambda x squared plus y squared. This is 25 minus 25, like this. Okay, so partial L over x, so 8x minus 4y plus, okay, 2 lambda x. Is that equal to 0? And partial L over partial y is negative 4x plus 2y plus 2 lambda y equal to 0. And partial L over partial lambda, that gives us the constraint, so equal to 0. Okay, so 3 equations, 3 unknowns, and we're trying to solve. Okay, so in the lecture and the other examples that I gave you, what I typically say is from equation number 1 or 2, you solve for lambda, and then you substitute in the other one. For example, solve for lambda from here, substitute here, so you'll get an equation in terms of x and y. Then together with the equation number 3, you can solve for x and y. But in this particular one, you can try that. You will see that it's actually end up with a somehow pretty complicated a set of nonlinear equations. Manually solving that actually is proved to be quite difficult. So in this particular case, we'll try slightly a different one here. Okay, yeah. So we can try this. Okay, from equation number 1. Okay, from equation 1, we can solve for the y at here. And y give us what? Give us 4y over there. So divided by 4, we have 2x plus 1/2 lambda x. Okay, and then we can sub into the equation number 2, sub this y over here and over here. Okay, yeah. So negative 4x plus 2x plus 1/2 lambda x plus 2 lambda and 2x plus 1/2 lambda x equal to 0. Okay, So there are 2, 4, so you can simplify that a bit of here. Negative 4, 2x plus 2x plus 1 half lambda x plus lambda 2x plus 1 half lambda x. And this lambda will cancel, this negative 2x will cancel this, okay? So that give us 1 half lambda x, and over here 2 lambda x plus 1 plus 1 half lambda square x, okay? Yeah. So there's a common factor x, so take out x. Inside here, so 1 half lambda plus 2 lambda, that's 5 over 2 lambda plus 1 half lambda square equal to 0. So this quadratic one is pretty simple. It's that you take out 1 half here, 5 lambda plus lambda squared, and take out the lambda here, plus 5 equal to 0. Okay, so now we got fairly easy equation in here. So this equal to 0 means x equal to 0 or lambda equal to 0, or lambda equal to negative 5. Okay, yeah. So x equal to 0, okay, if I sub x equals 0 into this, the equation that is here, so x equal to 0 here, you see the y will be 0, right? So for x equal to 0, okay, if I sub into 1, that's the stationary. Basically, that's the first derivative stationary point. Sub into 1, we get to y equal to 0. So you get a location x equal to 0, y equal to 0, 0, 0. So 0, 0, apparently it's not on the constraint, the circle there. So that's not the realistic solution. So this is basically not possible. Okay. So now let's look at the values of solution towards lambda equal to 0 and lambda equal to this. So for lambda equal to 0, okay, so what do we have then? What we can do is we can substitute same thing into let's just see where. We can substitute into equation number 1, 0, lambda. So we end up with what? Ax equal to 4y, y equal to 2x. Okay. So sub into 1, we have y equal to 2x. Okay. So now we can sub this one, okay, and sub into the constraint. Okay, sub into constraint here. So now what do we have here? Okay, so we'll have x squared plus 2x squared equal to 25, and that gives us x equal to positive negative root 5. Okay, yeah, which means y equal to 2x, so y, okay, so y will be 2 positive negative 2 root 5, right? Yeah. So essentially, we got a pair of points here is one pair is root 5 for x, and the other y is positive this, and the other one is negative root 5 and negative 2 root 5. So at these two locations, these are two stationary points. Maybe they're corresponding max, or maybe they're corresponding mean for the temperature, right? So but we have to calculate afterwards. But anyway, so this is what we get corresponding to lambda equal to 0. So same thing for lambda equal to 5. You can do a similar approach. Okay, for lambda equal to 5, you can negative 5, right? What's going here? So negative 5 here. Okay, so negative 5. Let's see, what can we do? Maybe we can try either one of these. If I control 5 at negative 5 here, so 2 times negative 5, negative 10x. So ax minus negative 10x is 10 plus negative 10x is negative 2x. So negative 4y minus negative 2x. Okay, so that's what you get there. So sub into 1, and we have, what do we have again? Sorry, where is it? Yeah, so ax, maybe write it down, ax minus 4y, okay, ax minus 4y minus 10x equal to 0, so give us negative 2x minus 4y equal to 0. So y equal negative, okay, 1 half x. Okay, so subbed into the constraint. Okay, so x squared plus 1 half x squared equal to 25. So now you can solve same thing. So this solution for the x is positive and negative root 2 root 5. Okay, so for when x is positive 2 root 5, we have y equal to, so over here, so negative root 5. And when x is negative 2 root 5 and y equal to positive root 5. Okay, so essentially we have another pair of locations which are stationary here. So then the last step you do is you can try to substitute the values, right? Substitute this, and this and that into the temperature function, okay, and here to see what are the temperatures. So technically what you can do is, we can do a secondary test to verify whether there's maximum minimum, but in this case we'll use the trial and errors, which basically we say, okay, at the t at this location, okay, turn out to be 0, and you can also see that same thing for this location, okay, and you will see that at this location it's 125, okay, and the same as this location. Okay, so apparently this is a mean, this is a max. Okay, so there are two mean locations, two max temperature locations. So that's one way of solving this question right here. Okay, so you can also try this. I from equation number 1 solve for the y. You can also try from equation number 2 solve for y and then substitute in equation number 1. So you will get the same answers. All right, yeah. So that's the end of this here. Okay, let me know if you have any questions. Thank you.